In this tutorial, we will be discussing nuclear chemistry, in particular the different particles that are emitted in nuclear reactions. So when we're looking at a symbol for a compound, you'll notice that there's always the symbol of the element, which could be one or two letters depending on what element it is. On the bottom is the number of protons. The number of protons and that letter will always go together 100% of the time. So if this number changes, then the letter will change as well. The atomic number dictates what element it is. Up here, this is the mass number. That's the protons and the neutrons. So it's the number on the bottom added to the number of protons. So isotopes and radiation. Once we get past 20, there's usually at least one or two isotopes that are not stable, which means that they will end up decaying. So these particles that are emitted in this decay is called radiation. So in those particles we have alpha particles, beta particles, positrons, and gamma rays. Those are the four particles that we will be discussing. So an isotope of an element that emits radiation is called a radioisotope. When radiation is emitted, a radioisotope may undergo changes from the number of protons or converted from one atom to another element. So you're changing what element it actually is because the protons are changing. The protons always dictate what element it is. That's not going to happen all the time, but it does happen frequently. So once again, the mass number is on the top, which is the protons and the neutrons. The protons are on the bottom. The mass number is the atomic number plus however many protons there are. So the atomic number is always going to be smaller. And then you have the letters for the element. Now, if we were to shortcut it, it's the name of the element dash the mass number. So 131 is the mass number, so it would be iodine 131 or I-131. So here are just some few examples. So if we look at magnesium, there are two radioactive isotopes with magnesium. One with 23 protons and neutrons, and one with 27 as the mass number. Iodine, notice the bottom number is always 53. It could have a mass number of 125 or 131. Alright, so here we're going to go through the different types of radiation that you could possibly go through. Now, there are more than this, but these are the four basics. We have alpha, which is the biggest. It has 2 protons, and then it has 2 neutrons, so that's why the top number is 4, because it's the protons and the neutrons added together, just like a mass number. So the top number is 4, and then 2 is the number of protons, and then we abbreviate it with He, because if you look on the periodic table, helium is the second element. It has 2 protons. The beta is way smaller. Notice that there's no mass to it whatsoever. So the mass number is 0. Its bottom number is actually -1. It's actually an electron that comes out of the nucleus, which seems odd, but that is how it works. A positron is the exact opposite of the beta, because it has a +1 at the bottom rather than a -1. Once again, this one is abbreviated with an E. Notice over here, it could be abbreviated with a B plus for beta plus. Over here, the beta is also abbreviated with just a letter B, or a beta. And then gamma rays actually are just energy. It's energy that comes out. So here's the summary of the 4 different types. Plus, we have a few more. We have the proton and the neutron added in there as different particles in the nucleus. These get smaller as you go down, which actually does have an impact. The smaller it is, the harder it is to stop that radiation. Alright, so if we look at trying to do symbols, alpha radiation could be just an alpha symbol, or it could be 4/2 He. Radiation with a mass number of 0 with a positive 1 charge, that would be the positron. Or you could do the beta with a plus. Radiation that represents high energy radiation released from the nucleus, that's the gamma. Now once again, that's 0/0. Alright, so when radiation strikes a molecule, it can knock electrons away, forming unstable ions. So it makes the compound break down. It could also interact with water molecules, removing electrons and producing H2O+, which is rather unstable. We typically see that plus sign with H3O+. Notice that 3 and the 2, that's a huge difference in the stability, because then it creates undesirable chemical reactions that then react with things that we don't want it to react with. Cells most sensitive to radiation are those that undergo rapid cell division. In other words, they reproduce really fast. That's bone marrow, skin, reproductive cells, and cancer cells. Those are the most prone to have cancer issues. So radiation protection, notice the smaller the radiation, the harder it is to protect. The alpha particle can be good with just paper or clothing. That's the biggest. Whereas when we start getting into gamma rays, which is pure energy, you need a lead shield or a concrete wall to protect you. So how you can protect yourself is limiting the amount of time near radioactive sources and increasing the distance from the source. So you just simply move away from it. If we look at the 3, alpha, beta, and gamma, notice how much further the gamma can flow through the air and how much it can penetrate the tissue. Here it's 0.05 millimeters, 50 centimeters it can go through. So the smaller it is, the harder it is to stop it. And that is your overview of the particles of radiation.